Hello, in this lecture, we're going to discuss the central limit theorem, a theory that is very fundamental in the study of inferential statistics. Let's first discuss a couple of concepts. First concept, sampling distribution of the sample mean. This defined as the distribution of sample means from successive samples of a certain size. Let me explain what I mean here. Let's say that we have a population distribution. You see, I'm very specific when I come to label this graph. The horizontal axis is labeled as x. This means that this is a distribution of variable x, and the mean is mu, and that means that this is a population mean. In other words, we are looking at a distribution of a variable x for the entire population of a variable x. Okay. So this is a population distribution. Now, from this population distribution, we take many samples of a certain size. That is, all the samples we take should have the same size. You take many samples. And every time you take a sample, you calculate the sample mean. And you will have many sample means of the same size. Now, all these sample means of the same size will form a new distribution. Again, I'm very specific about labeling this graph. The horizontal axis is labeled as m, meaning that this is a distribution formed by sample means of the same size. In addition, here is the mean of sample means is labeled as mu sub m. M part means that this is a formed by all sample means, but the mu part means the mean of sample means. Okay. Now this distribution has a name. It is called sampling distribution of the sample mean because it is formed by sample means, and we get those sample means by taking samples. So this sampling process. Now, second concept, the theoretical sampling distribution of the sample mean, and this is defined as the distribution of all sample means of a certain size. Again, from this population, we take samples, but this time we take all possible samples of a certain size. You take all possible, you exhaust all possible samples of the same size. Okay. Then, every time you take a sample, you calculate the sample mean. So you end up have all possible sample means of a certain size. All these sample means of a certain size form a new distribution with the mean of a sample mean, and the way I label this horizontal axis again means that this is a distribution formed by all sample means. This distribution has a name. It is called the theoretical sampling distribution of the sample mean because it contains all possible samples of the same size, of a certain size. And that's why it's called theoretical sampling distribution of the sample mean. In reality, it's a lot of times it's impossible to obtain all possible samples of the same size because sometimes the population is very large, and all the possible samples from a large population is impossible to obtain. And that's why we can only theoretically derive as a result. And that's why we call it theoretical sampling distribution of the sample mean. Anyway, it implies that within this distribution, it contains all possible samples of a certain size from a population. Now, the question is, what is the relationship between the population distribution and the theoretical sampling distribution of the sample mean? This is what the central limit theorem trying to answer. The relationship between the population distribution and the theoretical sampling distribution of the sample mean. Now let's look at the central limit theorem. If all samples of size n are drawn from a population with the mean mu and the variance sigma squared, we know that this is a notation we use to indicate the population variance. Okay. 1a, if the population is normal, the theoretical sampling distribution of the sample mean is normal for all sample sizes. That is, if this is a population which is normal, if you take all possible samples of a certain size and calculate the sample means, and all sample means of the same size will form a theoretical sampling distribution of the sample mean, and this distribution is also normal in shape. And regardless the size, small size, large size, as long as the population is normal, the theoretical sampling distribution of the sample mean is also normal. So that's straightforward. Now, 1b, if the population is not normal, the theoretical sampling distribution of the sample mean approaches normal as the sample size increases. Now, if this is a population distribution, obviously it has a non-normal shape. If you take all possible samples of a certain small size, okay, how small? How to say? 2 or 3, sometimes 5, small size. And you end up have all the samples of a certain size, small size. Then you calculate the sample means for all these samples. All these sample means of this small size will form a theoretical sampling distribution of the sample mean, and this shape will not be normal because the population is not normal. But if you increase the sample size, you take all possible samples of a larger size and calculate sample means, and all these sample means of a larger size will form another theoretical sampling distribution of the sample mean, and this distribution is, well, is more symmetrical. Now you take all possible samples of an even larger size, and therefore you have all the possible sample means of a larger size, and all these sample means of a larger size form a new theoretical sampling distribution of a sample mean, and this shape is even more normal. You keep doing that, and you keep increasing sample size, and the shape of the theoretical sampling distribution approaches normal when the sample size increases. So that's what 1b says. 2. The mean of the theoretical sampling distribution of the sample mean equals the population mean. Okay. Mu sub n, the mean of theoretical sampling distribution of a sample mean, is identical to the mean of the population. This is the population distribution. This is the central place, central point of the distribution. The theoretical sampling distribution of the sample mean is distributed here. The central positions of the two distributions are the same. That is what this statement means. They are aligned along the same position. Okay. 3a and 3b, I put these two together because variance and the standard deviations are closely associated with each other. 3a, variance of the theoretical sampling distribution of the sample mean equals the population variance divided by the sample size. This is the variance of the theoretical sampling distribution of the sample mean. We know variance is a indicator of variations in a distribution of the spread, similar to the standard deviation. Okay, the standard deviation and the variance are all description of the spread. What is the spread? Look at this distribution. The population distribution has a spread, and this spread is described by the standard deviation of the population. This is the theoretical sampling distribution of the sample mean. It is also has a spread, variations, and this variation is described by the variance of the theoretical sampling distribution of the sample mean, or it can also be described as by the standard deviation of the theoretical sampling distribution of the sample mean. Okay, so that's the variation of the theoretical sampling distribution of the sample mean, the spread out, the width of the distribution. Okay. Now that the variance of the theoretical sampling distribution of the sample mean is equals the population variance divided by the sample size. 3b, standard error of the mean, which is the same thing as the standard deviation of the theoretical sampling distribution of the sample mean. Basically the same thing with two different names. This equals population standard deviation divided by the square root of sample size. Standard deviation of the theoretical sampling distribution of the sample mean, or the standard error of the mean, equals the population standard deviation divided by the square root of sample size. This is the population distribution. We use this symbol to indicate that this is a normal distribution with the mean mu and standard deviation sigma. This is a theoretical sampling distribution of the sample mean. We use this to indicate that this is also a normal distribution with his own mean and his own standard deviation. The mean of the theoretical sampling distribution of the sample mean is expressed as mu sub m. As we know that this number, this value is the same as this value. Between this value and this value, there is a relationship such as this. So this value can be calculated by using this value divided by the square root of sample size. This one. Okay. Population standard deviation divided by the square root of sample size. Now, if you look at these two expressions, this expression and this expression, can you tell the difference and similarities? You see, between this distribution and this distribution, these two values are the same. They are identical. The mean of the population equals the means of theoretical sampling distribution of sample mean. That's why they are at the same central location right here. Okay. What about this value? This value compared with this value. This value is obtained by using this value divided by the square root of sample size. Now, which value is bigger? This is bigger or this is bigger? This bigger. This bigger. Okay. Square root of n, the smallest sample size is 2. You cannot have a sample and the sample size 1. The smallest sample size is always 2. Square root of 2 is 1.41, larger than 1. So you have a number larger than 1 divided into this number, divided into this number. That's how you obtain this value. Therefore, this value is always smaller than this value. Okay. What does this mean? This value indicates the spread of distribution. This value indicates the spread of this distribution. If this value is smaller than this value, that means the spread of this distribution is smaller than the spread of this distribution. That's why every time when I draw these two distributions, I always draw the distribution of the theoretical sampling distribution of the sample mean is narrower than the population distribution. And that is because of this relationship. Okay. So now we discuss the central limit theorem that describes the relationship between the two sides of distribution. Let's now briefly summarize the relationship. From this population, we draw all possible samples of a certain size, and we obtain all sample means of a certain size. All the sample means of this certain size form the theoretical sampling distribution of the sample mean. The mean of the population equals the means of the theoretical sampling distribution of the sample mean. The variance of the theoretical sampling distribution of the sample mean equals the population variance divided by the sample size. The standard deviation of theoretical sampling distribution of the sample mean, or the standard error, equals the population standard deviation divided by the square root of sample size. In terms of shape, if the population is normal, the theoretical sampling distribution of the sample mean is normal regardless the sample size. If the population is not normal, the theoretical sampling distribution of the sample mean approaches normal when the sample size increases. Okay. Now let's use one example to test your understanding of the central limit theorem. We have a population which is normal with a mean 95, standard deviation 12. This is the population. Two questions. First, what is the shape of the theoretical sampling distribution of the sample means? Let's say sample size is 7. What's the shape? Normal or not normal? Second question, what are the mean, variance, and the standard error of the theoretical sampling distribution of the sample mean respectively? First, the shape of the theoretical sampling distribution of sample mean is normal. Why normal? Because population is normal, therefore the theoretical sampling distribution of the sample mean is also normal, regardless the sample size. Now, what is the mean of the theoretical sampling distribution of the sample mean. The mean is 95. Why? Because the population mean is 95. Therefore, the mean of the theoretical sampling distribution of the sample mean is also 95. What about the variance of the theoretical sampling distribution of the sample mean? According to central limit theorem, the variance of the population divided by the sample size equal to the variance of the theoretical sampling distribution of the sample mean. What is the population variance? We only have the value of population standard deviation. What is the population variance? The population variance is the squared of the population standard deviation. Okay? If this is the formula, the variance of the theoretical sampling distribution of the sample mean equals the population variance divided by the sample size. The population variance is the squared of population standard deviation. Okay, so population standard deviation 12, the square of 12 is 144, and 144 divided by the sample size, that gives us 20.57, which is the variance of the theoretical sampling distribution of the sample mean. Finally, what is the standard error? Standard error is the population standard deviation divided by the square root of sample size. 12 divided by the square root of 7, 4.54. Okay, and this is the distribution. This is the theoretical sampling distribution of the sample mean. Okay, look at this symbol. This is the normal. The mean 95, which is identical. They are located, centered on the same point. Here is important. For the population, the spread is 12. For the theoretical sampling distribution of the sample mean, the spread is only 4.54. That's why this is a much narrower distribution than this distribution. Okay, so this is a discussion of the central limit theorem. The in-class activity number 10 and 11 are closely associated with this discussion. So you can go ahead to do that two in-class activity, and also you can do the assignment 10 and 11. I hope this helps. I see you next time. Goodbye.